Right now, at this very moment, somewhere on our beautiful planet, the ocean is breathing. Vast currents of warm water are rising into the air, spinning slowly, gathering strength not through violence, but through the patient, ancient dance of water and wind. These aren't the destructive forces we often think of. These are hurricanes in their purest form, magnificent spirals of energy that reveal some of nature's most elegant secrets. Welcome to Sleep About Science. Tonight we're exploring the surprisingly gentle world of hurricanes. Not as disasters, but as marvels of atmospheric poetry. And if you drift off to sleep while listening, that's perfectly wonderful. These storm systems will continue their graceful dance whether you're awake or dreaming. Before we begin, please make yourself comfortable. Pull that blanket a little closer, adjust your pillow just right, and remember, this is educational content, not medical advice. If you haven't subscribed yet, you might want to, so you never miss these gentle journeys into science. Now, let me share something that might surprise you. Hurricanes are among the most organized, structured phenomena in all of nature. Far from being chaotic, they're actually demonstrations of perfect atmospheric order, spinning with a precision that would make the finest clockmaker envious. Picture this. A hurricane's eye can be so calm that birds have been observed flying peacefully within it, completely unaware of the circular walls of wind surrounding them. The eye of Hurricane Wilma in 2005 was so clear and still that pilots reported seeing stars through it, even during daylight hours. This isn't unusual, it's simply the hurricane showing us its quiet center, its peaceful heart. The word hurricane comes from Huracan, the Caribbean god of wind and storm. But long before humans gave these phenomena names, they were already practicing their slow, methodical dance. A single hurricane can contain more energy than all the electrical power generated by humans in an entire year, yet it moves across the ocean at the gentle pace of a leisurely bicycle ride, typically just 10 to 15 miles per hour. When hurricanes form, they begin not as violent storms but as gentle tropical waves, subtle ripples in the atmosphere that drift westward from Africa like slow, invisible ships. These waves are so mild that if you were standing beneath one, you might only notice slightly more clouds than usual, perhaps a gentle breeze. Yet within each wave lies the potential for something magnificent. The process of hurricane formation is called cyclogenesis, and it's remarkably similar to watching a ballet dancer begin to spin. The rotation starts almost imperceptibly, so slowly you might not notice it at first. The Coriolis effect, caused by our planet's rotation, gives each forming storm its direction. In the northern hemisphere, hurricanes always spin counterclockwise, while in the southern hemisphere, they spin clockwise. It's as if the Earth itself is choreographing these atmospheric dances. One of the most peaceful aspects of hurricanes is their predictability. Unlike sudden thunderstorms that can appear and disappear within hours, hurricanes announce themselves days or even weeks in advance. Meteorologists can track a hurricane's progress across thousands of miles of ocean, watching it develop and strengthen with the patience of gardeners tending to a slowly blooming flower. The eye of a hurricane is typically 20 to 40 miles across, large enough that if you were standing in the center, the walls of the eye would be beyond the horizon. Within this space, winds are typically less than 15 miles per hour, gentler than a typical spring breeze. The air pressure is so low that people often report feeling physically lighter, as if the storm is giving them a brief respite from the weight of the atmosphere itself. Hurricane hunters, the brave pilots who fly directly into these storms, often describe the eye as one of the most beautiful sights in nature. Imagine a perfect cylinder of clear blue sky, extending from the ocean surface up to heights of 8 or 9 miles, surrounded by towering walls of clouds that spiral upward like a natural cathedral. The ocean below is often surprisingly calm, with long, smooth swells rather than the choppy waves you might expect. The eye wall, the circular barrier of clouds surrounding the eye, is where the hurricane's strongest winds reside. But even here, there's an elegant structure. The clouds don't rise chaotically. They ascend in perfect spirals, like smoke from a very slow, very large campfire. The wind flows in organized bands, each layer moving at slightly different speeds, creating a complex but orderly system that can be beautiful to observe from space. Hurricanes are incredibly efficient at their primary job, moving heat from warm ocean waters toward the cooler upper atmosphere. Think of them as the planet's air conditioning system, working slowly but steadily to balance temperatures across the globe. A single hurricane can move as much heat away from the ocean as would be generated by burning millions of tons of coal, yet it does so using only the power of evaporating water and condensing vapor. The rainfall from hurricanes, while often abundant, follows remarkably organized patterns. The heaviest rain typically falls in spiral bands that rotate around the eye, creating a pinwheel pattern that can be stunning when viewed from satellite imagery. These rain bands can extend for hundreds of miles from the storm's center, but they're not random. They follow precise mathematical curves called logarithmic spirals, the same elegant shapes found in Nautilus shells and galaxy arms. One fascinating aspect of hurricanes is their relationship with dust. Many hurricanes that affect the Atlantic begin their journey influenced by dust clouds from the Sahara Desert. This dust, carried thousands of miles across the ocean, can actually suppress hurricane formation when concentrations are high. The dust particles interfere with the storm's development, acting like nature's own hurricane suppression system. The ocean beneath a hurricane undergoes remarkable changes. The storm's circulation creates upwelling, cooler water from deeper layers rises to the surface, bringing nutrients that will later support marine life. In this way, hurricanes are like slow-moving plows turning over the ocean and enriching its surface waters. Some marine biologists refer to hurricane paths as underwater gardens, areas where sea life flourishes in the storm's wake. Hurricanes have their own internal weather systems. Within the larger circulation, smaller whirlwinds called mesovortices can form tiny spinning systems within the larger spin, like wheels within wheels. These are typically only a few miles across and can be detected by sophisticated radar systems. They add another layer of elegant complexity to the hurricane structure. The sound of a hurricane, according to those who have experienced the eye wall, is often described not as a howl or scream, but as a deep, constant hum, almost like the sound of the ocean heard from far away. This sound is created by wind moving over and around objects, creating resonant frequencies that can be surprisingly musical. Some survivors describe it as similar to a massive organ playing a single low note. Temperature distribution in hurricanes follows beautiful concentric patterns. The eye is typically the warmest area aloft, while the eye wall contains the coolest temperatures at the surface. This temperature gradient drives the storm's circulation, creating natural convection currents that rise and fall in organized patterns. It's like a massive slow-motion version of the convection you might see in a pot of gently simmering water. Hurricanes can live for weeks, slowly traveling thousands of miles across ocean basins. Hurricane John in 1994 lasted for 31 days and traveled over 7,000 miles, roughly the distance from New York to Mumbai. Throughout its long journey, it maintained its essential structure, like a living thing migrating across the ocean. Some hurricanes have traveled so far that they've crossed from one ocean basin to another, changing their names as they cross international boundaries. The pressure changes within hurricanes create what meteorologists call the stadium effect. If you could see air pressure as physical structures, the eye would look like a deep bowl or stadium, with the eye wall forming steep sides. The lowest pressure ever recorded in a hurricane was 870 millibars in Hurricane Tip in 1979, a pressure so low that it's similar to what you'd experience at an altitude of over 4,000 feet. Hurricanes influence cloud formation hundreds of miles away from their centers. The storm's circulation can suppress or enhance cloud development across vast areas, creating clear skies in some regions and increased cloudiness in others. This influence can extend across entire ocean basins, with a single hurricane affecting weather patterns from the Caribbean to Europe. The lifespan of a hurricane follows a predictable pattern that meteorologists call the hurricane life cycle: birth, growth, maturity, and decay. Each phase has its own characteristics and beauty. During the decay phase, hurricanes often create spectacular cloud formations as their organized structure gradually dissolves back into ordinary weather systems. This process can take several days, during which the storm slowly unwinds like a clock spring releasing its energy. Wind shear, the difference in wind speed and direction at different altitudes, can dramatically affect hurricane development. Light wind shear allows hurricanes to grow and strengthen, while strong wind shear can prevent formation or weaken existing storms. It's like trying to build a tower of blocks in a gentle breeze versus a gusty wind. The calm conditions allow for better organization and structure. The spiral arms of hurricanes follow mathematical principles discovered by ancient scholars. The shape is known as a logarithmic spiral or equiangular spiral, and it appears throughout nature in flower petals, shell patterns, and galaxy formations. That a hurricane structure follows the same mathematical rules as a sunflower's seed arrangement or a chambered nautilus shell speaks to the fundamental order underlying apparent chaos. Hurricanes can trigger bioluminescence in ocean waters. The storm's churning action disturbs microscopic marine organisms called dinoflagellates, causing them to emit blue-green light. Satellite images sometimes capture this phenomenon, showing hurricanes surrounded by faint, ethereal, glowing waters. It's as if the ocean itself is celebrating the storm's passage with gentle fireworks. The forward speed of hurricanes varies dramatically depending on their location and the surrounding atmospheric conditions. Some hurricanes crawl along at just 2 or 3 miles per hour, slower than a typical walking pace, while others can accelerate to over 60 miles per hour when they encounter strong steering currents. The slower-moving storms often produce the most rainfall, as they have more time to draw moisture from the ocean and release it over land. Hurricane formation requires ocean water temperatures of at least 80 degrees Fahrenheit, but not just at the surface. The warm water must extend down to at least 150 feet deep to provide enough fuel for storm development. This creates natural barriers to hurricane formation, early in the season when deep ocean waters are still cool, or late in the season when the sun's angle is too low to maintain the necessary temperatures. The eye wall replacement cycle is one of the most fascinating aspects of mature hurricanes. Periodically, the eye wall will collapse and be replaced by a new one that forms from outer rain bands. During this process, the hurricane typically weakens temporarily, then often strengthens again with its new eye wall. It's like the storm is renovating itself, rebuilding its core structure to continue its journey. Hurricanes interact with the upper atmosphere in ways that can influence weather patterns thousands of miles away. Their circulation can affect the jet stream, creating what meteorologists call teleconnections, long-distance atmospheric relationships that link weather in one part of the world to weather in another. A hurricane in the Atlantic, for example, might influence rainfall patterns in Europe or temperature patterns in Asia. The energy source for hurricanes is the latent heat released when water vapor condenses into liquid water. Every gram of water vapor that condenses releases the same amount of energy that was required to evaporate it in the first place. Over the warm ocean, millions of tons of water are constantly evaporating and condensing, creating an enormous renewable energy source that can power a hurricane for weeks. Hurricanes create their own weather modification effects through a process called cloud seeding. The storm's circulation lifts salt spray and other particles high into the atmosphere, where they serve as condensation nuclei for cloud formation. This natural cloud seeding can affect precipitation patterns across large areas, sometimes increasing rainfall in regions far from the storm center. The beautiful spiral structure of hurricanes is maintained by a delicate balance between two forces: the inward flowing air trying to reach the low-pressure center, and the Coriolis effect deflecting that air to the right in the northern hemisphere. This balance creates the elegant curved bands that spiral inward like water flowing down a drain, but in slow motion and on a scale hundreds of miles across. Hurricane-generated waves, called swells, can travel thousands of miles from their source. These waves are often the first sign of a distant hurricane, arriving at coastlines days before the storm itself. Surfers and sailors learn to read these swells, recognizing the long, regular patterns that indicate a hurricane's presence somewhere far out at sea. The waves can be remarkably uniform, arriving with the consistency of a slow oceanic heartbeat. The vertical structure of hurricanes is as impressive as their horizontal extent. These storms can reach heights of over 50,000 feet, nearly twice the cruising altitude of commercial aircraft. The ascending air within the storm creates a natural elevator system, carrying moisture and energy from the ocean surface to the very top of the troposphere, where it's released and spreads outward in all directions. Hurricanes have distinct seasons in different ocean basins. The Atlantic hurricane season runs from June through November, with peak activity typically occurring in late August and early September. But in the southern hemisphere, hurricane season runs from November through April. This global timing means that somewhere on Earth it's almost always hurricane season, with these magnificent storms forming and dissipating in a planetary rhythm. The naming of hurricanes follows carefully maintained international lists that rotate every 6 years. Names are chosen to be short, distinctive, and culturally appropriate for the regions where the storms occur. When a hurricane causes significant damage or loss of life, its name is retired from future use, like retiring the jersey number of a distinguished athlete. This creates a historical record embedded in the naming system itself. Satellite imagery has revealed that hurricanes often contain features called hot towers, intense thunderstorms within the overall circulation that can reach heights of over 50,000 feet. These towers appear as bright spots on infrared satellite images and are indicators of a hurricane's intensity and organization. They're like skyscrapers within the hurricane's cityscape of clouds. The ocean's response to hurricanes includes the formation of cold wakes, trails of cooler water left behind as the storm moves. These wakes can persist for weeks after a hurricane passes, and they affect the development of subsequent storms that might follow the same path. It's as if each hurricane leaves its signature written in the ocean's temperature patterns. Hurricane rainfall follows predictable patterns based on the storm's structure and movement. The heaviest rain typically falls to the right of the storm's track in the northern hemisphere, due to the interaction between the hurricane's circulation and its forward motion. This creates natural patterns that meteorologists can use to predict flooding risks hours or days in advance. The atmospheric pressure changes associated with hurricanes can be detected by sensitive instruments hundreds of miles away from the storm. These pressure waves, called gravity waves, ripple outward from the hurricane like the waves you might create by dropping a stone in a still pond. Scientists use these waves to study hurricane structure and intensity from great distances. Hurricanes can influence the Earth's rotation through their interaction with ocean currents and atmospheric circulation. While the effect is extremely small, measured in microseconds, it demonstrates the profound connection between these storms and the planet's fundamental physical processes. Each hurricane is, in its own tiny way, participating in the ancient dance of planetary motion. The development of hurricane reconnaissance aircraft has allowed scientists to study these storms from within, flying directly into hurricanes. These aircraft collect data that helps meteorologists understand storm structure and behavior. The pilots and scientists who undertake these missions often describe the experience of flying through the eye wall and into the calm eye as one of the most remarkable experiences of their careers. Hurricane storm surge is created by the storm's winds pushing ocean water towards shore, but also by the low atmospheric pressure literally pulling water upward. This creates a dome of elevated water that moves with the storm. The surge is highest in the right front quadrant of the hurricane, where the storm's forward motion and circulation work together to maximize the water's height. The formation of tornadoes within hurricanes is a common occurrence, but these tornadoes are typically weaker and shorter-lived than those that form in supercell thunderstorms. Hurricane-spawn tornadoes are usually classified as EF0 or EF1 on the enhanced Fujita scale, and they're often difficult to detect because they're embedded within the larger circulation of the hurricane itself. Hurricanes can trigger earthquake activity in rare circumstances, particularly when they pass over areas with existing geological instability. The combination of atmospheric pressure changes and ground loading from heavy rainfall can sometimes provide the small additional stress needed to trigger earthquakes that were already close to occurring naturally. The interaction between hurricanes and land surfaces creates unique microclimate effects. Coastal forests can channel hurricane winds in unexpected ways, creating areas of increased or decreased wind speed based on topography and vegetation patterns. These effects can be predicted using computer models that account for surface roughness and terrain features. Hurricane lightning is typically less frequent than in ordinary thunderstorms, but when it does occur, it often follows distinctive patterns. Lightning activity tends to be concentrated in the outer rain bands and occasionally in the eye wall, but rarely in the eye itself. The lightning often appears as cloud-to-cloud discharges rather than cloud-to-ground strikes. The acoustic signature of hurricanes can be detected by specialized microphones called infrasound sensors. These instruments can pick up the low-frequency sound waves generated by hurricanes from thousands of miles away. The sound signature changes as the storm develops, providing another tool for monitoring hurricane intensity and structure. Hurricanes affect marine ecosystems in complex ways that scientists are still studying. While the immediate impact can be disruptive, many marine species have evolved to take advantage of hurricane-generated changes in water temperature, salinity, and nutrient distribution. Some fish species actually follow hurricanes, feeding on the organisms stirred up by the storm's passage. The clouds within hurricanes contain supercooled water droplets that remain liquid even at temperatures well below freezing. These droplets can instantly freeze when they encounter aircraft or other objects, creating ice formations that reveal the storm's internal structure. Hurricane Hunter aircraft often return from missions covered in ice formations that map the temperature and moisture patterns within the storm. Hurricane eyes can contain multiple vortices, smaller circulation centers that orbit around the main eye. These vortices can sometimes merge or split apart, creating complex internal dynamics within the larger storm system. Time-lapse satellite imagery of these processes reveals patterns that resemble celestial mechanics, with smaller circulations orbiting larger ones like moons around a planet. The rainfall distribution from hurricanes can be highly asymmetric, with some areas receiving minimal precipitation while others experience extreme amounts. This asymmetry is influenced by factors including the storm's forward speed, the surrounding atmospheric environment, and interactions with land surfaces. The heaviest rainfall often occurs in areas where the hurricane circulation interacts with existing weather patterns. Hurricane-generated ocean waves can cause what oceanographers call wave trains, sequences of waves that propagate across entire ocean basins. These wave trains can be detected by coastal monitoring stations weeks after the hurricane that created them has dissipated. The waves carry energy generated by the storm to distant shores, creating a physical connection between the hurricane and coastlines thousands of miles away. The thermal structure of hurricanes creates natural laboratory conditions for studying atmospheric physics. The clear air in the eye provides a window for observing the storm's internal processes, while the eye wall acts as a natural wind tunnel where scientists can study extreme atmospheric conditions. These observations have advanced our understanding of fluid dynamics and thermodynamics. Hurricanes can influence their own environment through a process called beta drift. The storm's circulation interacts with the planet's rotation in ways that cause the hurricane to drift northward and westward relative to the steering currents that would otherwise control its movement. This self-steering effect is most pronounced in storms that are not strongly influenced by other weather systems. The water cycle within hurricanes is intensely accelerated. Water evaporated from the ocean surface can be carried to great heights, condensed into clouds, precipitated as rain, and returned to the ocean all within a matter of hours. This rapid cycling can move enormous quantities of water. A single hurricane can evaporate and precipitate water equivalent to the flow of multiple major rivers. Hurricane eyes sometimes contain clouds that form at different levels, creating a layered structure that pilots describe as flying through multiple rooms in a vast atmospheric house. These stratocumulus clouds can form at various altitudes within the eye, driven by subtle differences in temperature and moisture at different levels of the atmosphere. The electromagnetic effects of hurricanes can be detected by radio equipment. The storm's electrical activity and the interaction between its circulation and the Earth's magnetic field can create radio signals that propagate for thousands of miles. Amateur radio operators sometimes use these signals to track hurricane positions and intensities. Hurricane seasons show long-term cycles that correlate with ocean temperature patterns and atmospheric circulation changes. The Atlantic multidecadal oscillation, for example, influences Atlantic hurricane activity on timescales of 20 to 30 years. These cycles help scientists understand natural climate variability and improve long-range seasonal forecasting. The pressure gradient within hurricanes creates natural experiments in atmospheric physics. The steep pressure gradients near the eye wall can exceed those found anywhere else in the atmosphere, providing unique opportunities to study how gases behave under extreme conditions. These observations have contributed to our understanding of fluid dynamics and atmospheric chemistry. Hurricane reconnaissance has revealed that storm cores often contain clear air columns that extend from the surface to great heights. These columns, visible on aircraft radar as echo-free regions, represent areas where air is descending within the eye. The descending air warms and dries, creating the characteristic clear, calm conditions that make hurricane eyes so distinctive. The interaction between hurricanes and the upper atmosphere can trigger the formation of gravity waves that propagate into the stratosphere. These waves can influence atmospheric chemistry and dynamics at altitudes far above the storm itself. Scientists study these effects to understand how hurricanes influence the global atmosphere beyond their immediate weather impacts. Hurricane rainfall patterns often reveal mathematical relationships that follow power laws and fractal geometries. The distribution of rainfall amounts across different scales, from individual rain gauges to entire river basins, shows statistical patterns that help meteorologists understand the fundamental processes governing precipitation in these complex systems. The ocean mixed layer depth changes dramatically during hurricane passage. The storm's winds and circulation can deepen the mixed layer from its typical depth of 100 feet to depths of 300 feet or more. This mixing brings cooler water to the surface and warmer water to greater depths, effects that can persist for weeks after the storm passes. Hurricane storm tracks often follow preferred pathways that meteorologists call storm highways. These pathways are determined by large-scale atmospheric patterns, ocean temperatures, and seasonal changes in the position of high and low pressure systems. Understanding these pathways helps forecasters predict where hurricanes are likely to travel. The formation of concentric eye walls in intense hurricanes creates double-walled structures that can be seen in radar imagery as nested circles of precipitation. The interaction between these eye walls affects the storm's intensity and structure in ways that scientists are still working to understand. These double eye walls often mark transitions in the storm's life cycle. Hurricane-generated turbulence can mix atmospheric layers that are normally stratified by temperature and density. This mixing can transport chemicals and particles between different levels of the atmosphere, affecting air quality and atmospheric chemistry over large areas. The effects can be detected by atmospheric monitoring stations hundreds of miles from the storm center. The heat content of ocean waters affects hurricane development more than surface temperature alone. Scientists measure ocean heat content by examining temperature profiles to depths of several hundred feet. This three-dimensional view of ocean thermal structure helps explain why some hurricanes intensify rapidly while others weaken unexpectedly. Hurricane eye wall clouds often exhibit mammatus formations, pouch-like structures that hang from the cloud base, like nature's chandeliers. These formations result from cold, dense air sinking within the cloud, creating the characteristic bulbous appearance that pilots and hurricane hunters often describe as one of the most beautiful cloud formations they encounter. The acoustic environment within hurricane eyes can be surprisingly quiet, with sound levels sometimes lower than those in a typical suburban neighborhood at night. This quietness results from the lack of wind and the insulating effect of the surrounding eye wall clouds, which absorb sound waves that might otherwise create noise within the eye. Hurricane-generated sea spray can be carried to great heights within the storm, sometimes reaching altitudes where commercial aircraft cruise. This spray contains salt and other ocean-derived particles that can serve as condensation nuclei for cloud formation, creating a feedback loop that can influence the storm's development and precipitation patterns. The mathematical models used to forecast hurricanes require some of the most powerful computers on Earth. These models solve millions of equations simultaneously, calculating the behavior of the atmosphere at thousands of points arranged in three-dimensional grids. The computational requirements are so intense that hurricane forecasting has driven advances in supercomputing technology. Hurricane research has revealed that these storms can influence weather patterns through teleconnections that operate on timescales of weeks or months. A hurricane in one ocean basin can affect the probability of storm formation in another basin, or influence seasonal weather patterns in regions thousands of miles away through complex atmospheric linkages. The spiral bands of hurricanes can extend for hundreds of miles from the storm center, but they're not continuous structures. Instead, they're made up of individual convective cells, discrete thunderstorms that form, mature, and dissipate within the larger spiral pattern. Time-lapse satellite imagery reveals these bands as dynamic, ever-changing structures. Hurricane eyes can contain phenomena called hotspots, areas of particularly warm air that can be detected by infrared satellite imagery. These hotspots result from intense subsidence or sinking air within the eye. The sinking air compresses and warms, creating temperature anomalies that can be several degrees warmer than surrounding areas. The study of hurricanes has contributed to our understanding of chaos theory and complex systems. Small changes in initial conditions can lead to dramatically different outcomes in storm development and behavior, illustrating the fundamental unpredictability that exists even within well-understood physical systems. Hurricane-generated lightning tends to occur in bursts that correlate with the storm's internal structure and development. These lightning patterns can provide insights into the storm's intensity and organization, offering forecasters another tool for monitoring hurricane behavior in real time. The ocean's response to hurricane passage includes the formation of internal waves, underwater waves that propagate along boundaries between water masses of different densities. These waves can persist for days or weeks after a hurricane passes, carrying energy throughout the ocean basin and affecting marine ecosystems far from the original storm track. Hurricane seasons in different ocean basins sometimes show inverse relationships, with active seasons in one region corresponding to quiet seasons in another. These relationships result from large-scale atmospheric and oceanic patterns that influence storm formation on a global scale, demonstrating the interconnected nature of Earth's climate system. The pressure changes associated with hurricane passage can affect sensitive instruments and biological processes. Migrating birds sometimes alter their flight patterns in response to approaching hurricanes, apparently sensing the pressure changes hours or days before the storm's arrival. Similarly, some plants and animals exhibit behavioral changes that correlate with hurricane approach. Hurricane reconnaissance aircraft use sophisticated instruments to measure not just wind speed and pressure, but also temperature, humidity, turbulence, and even the electrical properties of the storms they penetrate. These measurements have revealed the three-dimensional structure of hurricanes in remarkable detail, contributing to improved forecasting and scientific understanding. The interaction between hurricanes and climate change is an active area of research, with scientists studying how warming ocean temperatures and changing atmospheric patterns might affect hurricane frequency, intensity, and behavior. While the relationship is complex and still being understood, these studies contribute to our knowledge of how Earth's climate system responds to changing conditions. Hurricane formation requires not just warm ocean temperatures but also low vertical wind shear, adequate atmospheric moisture, and sufficient distance from the equator for the Coriolis effect to provide the necessary rotation. The combination of these factors creates natural laboratories for studying atmospheric dynamics under extreme conditions. The beauty of hurricanes, when viewed from space or through the sophisticated instruments that study them, reveals nature's capacity to create order from apparent chaos. These magnificent storms, with their perfect spiral structures and complex internal dynamics, demonstrate the elegant physics that govern our atmosphere and oceans. They remind us that even in nature's most powerful displays, there is structure, predictability, and profound beauty waiting to be discovered by those who take the time to look closely. Hurricane research has also revealed fascinating connections between these storms and other natural phenomena. The same fluid dynamic principles that govern hurricane formation also influence the rotation of galaxies, the formation of whirlpools, and even the spiral patterns in nautilus shells. This universality of physical laws demonstrates the deep mathematical order that underlies the apparent diversity of natural forms. The study of hurricane climatology has revealed long-term cycles and patterns that help scientists understand natural climate variability. The Atlantic multidecadal oscillation, a pattern of ocean temperature changes that occurs over 20–40-year periods, strongly influences Atlantic hurricane activity. During the warm phase of this oscillation, hurricane seasons tend to be more active, while the cool phase generally produces quieter seasons. Hurricane formation in the Pacific Ocean exhibits different characteristics than Atlantic hurricanes, partly due to the vast size of the Pacific Basin and different ocean temperature patterns. Pacific typhoons can grow larger than their Atlantic counterparts, with some storms reaching diameters of over 1,000 miles. The sheer scale of these Pacific storms demonstrates the enormous energy available in Earth's largest ocean basin. The interaction between hurricanes and the jet stream creates fascinating atmospheric dynamics that can influence weather patterns across entire continents. When a hurricane moves far enough north to interact with the jet stream, it can cause the jet to buckle and create downstream effects that influence weather from coast to coast. These interactions can trigger the formation of other weather systems or suppress them depending on the specific dynamics involved. Hurricane-generated gravity waves propagate through the atmosphere at the speed of sound, carrying information about the storm's intensity and structure to locations hundreds of miles away. These waves can be detected by sensitive barometers and can even influence the behavior of other atmospheric systems. The gravity wave field around a hurricane creates a kind of atmospheric fingerprint that reveals the storm's characteristics to distant observers. The role of hurricanes in the global water cycle is enormous. A single large hurricane can evaporate and transport more water than flows through all the rivers in the United States combined. This water is then distributed across vast areas as the storm moves and eventually dissipates, contributing to rainfall patterns that can affect entire continents. In this way, hurricanes serve as massive water distribution systems for the planet. Hurricane eye-wall replacement cycles demonstrate one of nature's most remarkable examples of self-renewal. When the original eye wall begins to weaken, the storm doesn't simply decay. Instead, it rebuilds itself with a new eye wall formed from outer rain bands. This process can occur multiple times during a hurricane's lifetime, allowing some storms to maintain their intensity for weeks as they traverse ocean basins. The thermal dynamics within hurricanes create natural heat engines of extraordinary efficiency. The conversion of latent heat energy stored in water vapor to kinetic energy in the form of wind represents one of the most efficient energy conversion processes in nature. This efficiency explains how hurricanes can maintain their intensity for so long while traveling thousands of miles across the ocean. Hurricane track forecasting has improved dramatically over the past several decades, with modern 5-day track forecasts being as accurate as 3-day forecasts were in the 1990s. This improvement results from better understanding of atmospheric dynamics, improved computer models, more accurate initial conditions from satellite and aircraft observations, and more powerful computers capable of running complex models quickly enough to be useful for operational forecasting. The acoustic signature of hurricanes includes both audible sounds and infrasonic waves below the range of human hearing. These infrasonic waves can travel for thousands of miles and are sometimes detected by monitoring stations around the world. The infrasonic signature can provide information about hurricane intensity and can even be used to track storms in remote ocean areas where other observations are unavailable. Hurricane-induced ocean mixing affects global ocean circulation patterns by redistributing heat and salt content throughout the ocean basins. The mixing brings cold, nutrient-rich water to the surface while pushing warm surface water to greater depths. This redistribution of ocean properties can influence currents that affect climate patterns around the world, demonstrating how hurricanes contribute to the global climate system. The formation of hurricane spiral bands follows the same mathematical principles that govern many rotating systems in nature. The angle at which the bands spiral inward is determined by the ratio of the storm's rotational speed to its radial inflow, creating logarithmic spirals that exhibit what mathematicians call self-similarity, the same pattern repeated at different scales throughout the storm. Hurricane research has contributed to advances in numerical weather prediction that benefit all areas of meteorology. The need to accurately predict hurricane behavior has driven improvements in computer models, data assimilation techniques, and atmospheric observation systems. These advances improve weather forecasting for everything from daily weather to seasonal climate predictions. The electrical properties of hurricanes create natural laboratories for studying atmospheric electricity. The charge separation within hurricane clouds can create electrical potentials of millions of volts, and the resulting lightning discharges help scientists understand fundamental processes of atmospheric electrical activity. Hurricane-generated lightning often exhibits unusual characteristics, including prolonged discharges and unusual spectral properties. Hurricane-generated waves can achieve extraordinary heights through a process called wave focusing. When waves generated by different parts of the hurricane converge, they can create individual waves that greatly exceed the storm's average wave height. These rogue waves can appear suddenly and disappear just as quickly, creating hazards that can surprise even experienced mariners. The biological impacts of hurricanes extend far beyond their immediate path. Migrating birds can be carried hundreds of miles off course by hurricane winds, sometimes resulting in unusual species appearing in unexpected locations. These hurricane birds provide natural experiments in biogeography and help scientists understand how major weather events influence the distribution of wildlife. Hurricane eye-wall mesovortices can create localized areas of extreme damage even within storms that are not particularly intense overall. These small-scale rotating systems, typically only a few miles across, can produce winds that exceed the storm's overall rating and create damage patterns that appear almost tornadic in nature. Understanding these features is crucial for improving damage assessment and engineering standards. The interaction between hurricanes and topography creates complex wind patterns that can vary dramatically over short distances. Mountains can channel and accelerate hurricane winds in some areas while providing shelter in others. Coastal features like bays and peninsulas can similarly modify wind patterns, creating localized areas of enhanced or reduced wind speeds that can significantly affect damage patterns. Hurricane seasonal prediction has become increasingly sophisticated, incorporating factors ranging from ocean temperature patterns to solar activity cycles. These seasonal forecasts, issued months before hurricane season begins, help emergency managers and coastal communities prepare for potentially active seasons. While they cannot predict individual storms, they provide valuable guidance for resource allocation and planning. The study of paleohurricanes, prehistoric hurricanes recorded in geological and biological archives, reveals that hurricane activity has varied considerably over long time periods. Sediment cores from coastal lakes and coral growth patterns provide records of hurricane activity extending back thousands of years, helping scientists understand natural climate variability and place modern hurricane activity in historical context. Hurricane-generated storm surge can persist for many hours after the storm's passage, creating prolonged flooding that can be more dangerous than the wind itself. The surge doesn't simply retreat when the storm passes, it must find its way back to the ocean through whatever channels are available, often creating swift currents that can persist for hours or even days after the hurricane has moved on. The formation of concentric eye walls in major hurricanes creates what meteorologists call annular hurricanes, storms with ring-shaped eye walls that can be remarkably persistent and difficult to forecast. These storms often maintain their intensity for extended periods and resist the environmental factors that typically cause hurricane weakening. The physical processes that create and maintain annular structure are still being studied. Hurricane reconnaissance technology continues to evolve, with new instruments providing unprecedented detail about storm structure and behavior. Tail-mounted Doppler radar on Hurricane Hunter aircraft can map wind patterns throughout the storm in 3 dimensions, revealing the complex circulations that drive hurricane intensity changes. These observations are immediately transmitted to forecast centers where they improve real-time analysis and prediction. The interaction between hurricanes and climate variability operates on multiple timescales, from the year-to-year effects of El Niño and La Niña to the multi-decadal oscillations in ocean temperature patterns. Understanding these interactions helps scientists separate natural climate variability from human-induced climate change and improve long-range forecasting of hurricane activity. Hurricane-induced rainfall patterns can be extremely complex, with the heaviest precipitation often occurring in areas that seem counterintuitive based on the storm's track. Orographic effects, where mountains force air upward, can enhance rainfall on the windward side of mountain ranges while creating rain shadows on the leeward side. These effects can persist for hundreds of miles from the storm center. The eye of a hurricane can sometimes contain multiple vortices that orbit around each other in complex patterns. Time-lapse satellite imagery reveals these vortices merging and separating in ways that resemble planetary motion or atomic structure. These multi-vortex structures can affect the storm's intensity and longevity, adding another layer of complexity to hurricane behavior. Hurricane research has revealed that these storms can influence their own environment through feedback mechanisms that either enhance or suppress their development. For example, the cooling of ocean waters beneath a slow-moving hurricane can limit further intensification, while the storm's circulation can also modify the atmospheric environment around it in ways that affect its future development. The mathematical complexity of hurricane prediction requires some of the most sophisticated computer models in all of science. These models must simultaneously solve equations governing atmospheric motion, thermodynamics, cloud physics, ocean interactions, and land surface processes. The computational requirements are so enormous that hurricane forecasting has driven advances in supercomputing that benefit many other fields of science. Hurricane-generated microseisms, very small earthquake-like signals caused by ocean waves, can be detected by seismometers thousands of miles from the storm. These signals provide another way to monitor hurricane intensity and location, particularly for storms over remote ocean areas. The microseismic signature of a hurricane can sometimes be detected even when the storm is not visible to satellites due to cloud cover. The future of hurricane research promises even more remarkable discoveries as new technologies become available. Autonomous aircraft and underwater vehicles can collect data in conditions too dangerous for human-crewed missions. Advanced satellite sensors can measure storm characteristics with unprecedented precision. Machine learning algorithms can identify patterns in vast datasets that might escape human notice, potentially revealing new insights into hurricane behavior and predictability. As you drift off to sleep tonight, perhaps you can imagine these great spiral systems moving slowly across our planet's oceans, carrying out their ancient role in the Earth's climate system. They are not just storms, but participants in the global circulation that shapes our weather, moderates our temperatures, and connects every part of our beautiful, dynamic planet. Each hurricane is both an individual phenomenon and part of a larger system, a temporary organization of air and water that emerges from the ocean's warmth and returns to the atmosphere's embrace. In their organized beauty, hurricanes remind us that nature operates according to mathematical principles that we are only beginning to understand. They demonstrate that complexity can emerge from simplicity, that order can arise from apparent chaos, and that the most powerful forces in nature often follow elegant, predictable patterns. They are teachers, showing us the fundamental physics of rotating fluids, the chemistry of phase changes, and the thermodynamics of heat engines. They are also reminders of our planet's dynamic nature, of the constant exchange of energy between ocean and atmosphere that drives our weather and climate. In their spiral dance across the ocean basins, hurricanes write temporary poems in clouds and wind, stories that last for days or weeks before dissolving back into the larger narrative of Earth's atmospheric circulation. Thank you for joining me on this gentle journey through the science of hurricanes. Whether you're listening from a cozy bedroom in Minnesota, a quiet apartment in Singapore, a peaceful evening in Lagos, or anywhere else in our shared world, I hope you found something to spark your curiosity and ease you toward peaceful sleep. If you enjoyed tonight's exploration, please consider subscribing to Sleep About Science, and let me know in the comments where you're listening from. I love hearing from our global community of curious minds. Share what aspect of hurricane science you found most fascinating, or what other natural phenomena you'd like us to explore together in future episodes. Sleep well, wherever you are. May your dreams be filled with the gentle spirals of nature's most magnificent storms, and may you wake refreshed and ready to see the world with fresh eyes. May you find in tomorrow's weather a reminder of the beautiful complexity that surrounds us every day, and may you carry with you a sense of wonder for the elegant physics that governs our atmosphere and oceans. Good night, dear listeners. Sweet dreams, and remember, somewhere on our planet right now, hurricanes are dancing their slow, graceful dance across the warm ocean waters, participating in the ancient rhythms that make our world the dynamic, living system we call home.